Organic Chemistry Part 2, Lewis structures and how to draw them. There are a set of rules. You can find them easily on the internet. They're often a little bit different from each other, but they all have the same basic structure of, first of all, we need to work out the number of valence electrons. Well, actually 0. Let's start with 0. We need to know what we're looking at. So we usually have a formula. Then we have 1, which is there. 1 usually count valence electrons, which are the ones on in the outer shell apart from the d electrons. Electrons. Whoops, that's a bit close. It doesn't work with d block elements, so we are mostly interested in s and p electrons there, and that always gives 8. So hence an octet rule. 2. So we would then have to work out how many would be needed to fill. Work out number to fill orbitals. And then 1 minus 2 divided by 2, in fact, is the number of bonds needed. Of bonds. And then we're on drawing the molecule. So once we've got that, we know how many bonds that we will have in total. And then we need to start putting the elements on our piece of paper. So first of all, we take the most electropositive or the least electronegative atom and we put it in the middle, and the other ones around it. Then we add the bonds, and then we add the electrons up to 8, and sometimes we end up with too many. Remembering that if there's a charge on our compound, on our molecule, or on our ion, that we have to take that into account when we determine the number of electrons that we have to deal with. So let's do an example. Let's do CCl2H2. So how many electrons have we got? We've got 4 from the carbon. We've got 7 from the chlorine, times 2. And we've got 1 from the hydrogen, times 2, which gives us 14, 18, 20 equals 20. Then how many do we need to fill it up? We would need 8 to fill this up. We would need 8 times 2 to fill this up. And we would need 2 times 2 to fill this one up. So that gives us 24 and 4, that's 28. 28. And 28 minus 20 gives us 8 electrons, divided by 2 gives us 4 bonds. 8 electrons difference here, so it's not equal to. 8 electrons difference here, which gives us 4 bonds, because we need 2 electrons per bond. Let's put our most electropositive atom in the middle, that's the carbon, put the others around it, ClH. We don't know the shape of the molecule till we've worked out what's left over. So let's put our 4 bonds in. We need 1 per atom anyway. So now we've got it all connected together. Where are we? So now we've got it all connected together. We can put the electrons in. Let's put the bonding electrons in first. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 electrons in the bonds. That means the carbon is happy, giving us 12 left over. The hydrogens have got 2 each, which is okay, because they're in the sort of 0th group and they only have 2 electrons, and the chlorines can be filled up to make their 8 we like to put our electrons in pairs because they otherwise behave as a lone pair. So there is our Lewis structure for dichloromethane. So taking water now as another example, we've got H, well, let's have 2H and 1O, because that's how it is. We've got 6 electrons and 1, so we've got 8, and we would like to have 8 and 2, so 8, 9, 10, 11, 12. We would like to have 12, which again gives us 2 bonds. Because we've got a 4 difference, that's unsurprising, we expect there to be 2 bonds. So we've got 8 electrons to put in. Let's put our oxygen in, let's put it straight to 2 hydrogens. And now we need to add some more things. So we need, let's make this oxygen happy first, so it's got 2, and it's now got 2, 4, 6, 8 electrons. The hydrogens are happy because they've only got 2, and we're all finished. Now we've discovered that we've got 2 lone pairs on our oxygen, which will distort this by Lewis laws into a tetrahedron. So we've got 2 lone pairs and 2 bonds, which is 4 things in different directions, and the most far apart they can possibly get would be a tetrahedron. Water is not quite tetrahedral because the lone pairs have a higher repelling force, they're closer to the oxygen than the bonds are. So as a final example, we'll do a phosphate anion because it's got a charge and more interesting things happen. So let's take our process. We need 5 electrons, or we have 5 electrons per phosphorus, and 6 electrons times 4 per oxygen, giving us 29. But we also have the charge of 3 minus, so that's plus 3, giving us 32 electrons to play with. Let's put that all in a box so that we can have it equal to that. We would like 8 electrons per oxygen and phosphorus, which means that we're missing 11, but we've got 3, so we're only missing 8, which divided by 2 means that we would have 4 bonds. So if we draw our structure, we have our phosphorus in the middle here, and we will put an oxygen in a square around it just because it's symmetrical, and draw 4 bonds, which is easy in that case. Our phosphorus, if we put the electrons in these bonds, has 8, and now we need to add the rest to get up to 32, which would put our oxygens on full as well. We don't have any left over, so that's good, and that would be our initial structure. However, we have a new rule that we have to now introduce, that the phosphorus could have more electrons because it's got d orbitals as well. So it should really have 8, but it can accept more electrons. And if we look at this, the phosphorus has it's 4 electrons around it, but it should have 5, so it's got a positive charge. And the oxygens have got 8 electrons around them, but but only 2 of them are in a bond. So it's got 6 electrons, and then it's got the whole bond extra, so it has a negative charge. And they're all the same. So all of our oxygens have a negative charge, and they're right next to a positive charge. That's a kind of unlikely situation. We can make it a little bit better by taking 2 of these electrons and the notation we had earlier. With a double arrow we can make a new bond, and that will take our negative charge and add it to the phosphorus as well. So if we resolve that, let's do it with one finger. If we resolve that, that gets rid of the lone pair. It gives us a new lone pair, a new structure with no charge on the phosphorus, no charge on this oxygen, and negative on these oxygens. That's the normal observable structure for, or the normal structure that people give for phosphate anions. If we do something else, so we could take this negative charge instead and put it in here. That would get rid of this negative charge, but it would make the phosphorus very unhappy. We can move this bond back out as well. So hang on, let's do that. Move the bond back out as well. Now let's resolve it. So that would take this negative charge and bring it all the way onto this oxygen out here. And it looks exactly the same, just rotated. So this zero charged oxygen can move around onto any of the oxygens. It's a resonance structure. What else do we need to do? So the other thing that I wanted to say right now is there is another notation very common in Germany that you might have seen with lines for lone pairs. We can use those as well. Or alternatively, try to be consistent in your diagrams, but as long as it is showing what is supposed to be there, it is still correct if it's an accepted notation. So dots are an accepted notation, lines are an accepted notation, and I also tend to draw sometimes a little ghost for a lone pair to denote the fact that it's in an orbital. But obviously it's better if we stay with the same notation on one molecule. Okay, that'll do for Lewis structure. There's plenty of information in the internet about this. This is a really easy subject to find on YouTube or on Wikipedia and things like that.